So thank you all very much for coming out today to our online mathematical physics seminar at Rutgers University. Today we have Ian Jauslin speaking about Bell's inequalities and quantum non-locality. So without further ado, why don't you take it away?
Thank you. Thank you so much, Larry, for the invitation and for organizing all of this. Thank you all for coming, virtually at least. So today I'm going to be talking about Bell's inequalities. There are some experts in the field of Bell's inequalities in the audience here. So if you have any questions, this is really the right place to do it, because the things that I don't know, you'll certainly get an answer to. So please feel free during this talk to interrupt, ask questions, whatever may come to mind. I'm going to do some blatant self-promotion / advertising. This talk is about Bell's inequalities. It's based on a couple of YouTube videos that I made in the fall of this previous year. And so for those of you who are interested and who think that this is interesting stuff and want to share it with perhaps less scientifically minded people, I put a link to my YouTube channel here. The videos are accessible to people who don't have a background in mathematics or in physics. So if you think that this should be shared, please feel free to do so. I also, whenever I give talks, I like to advertise my website here, where you can find more information about this topic. In particular, you have links to the videos. In addition, I put these slides on my website. So if you're interested in following the various web links that I have here, please feel free to connect to my website. And there's plenty of information about my research and about other things that I've been doing. Okay, but without further ado, let me get started with the main content. So about Bell's inequalities. And I wanted to start this with a brief introduction, just to introduce what I'm going to be talking about and why I think it's important. So as the title suggests, I'm going to be talking about Bell's inequalities, or more precisely, I'm going to be talking about Bell's theorem. Bell's inequalities is a fairly old story that starts with a paper by John Bell from 1964, but it's also had a number of new developments that have followed that paper. And in fact, there are several different versions, several different formulations of Bell's inequalities, and several different formulations of Bell's theorem that have come out in subsequent years. In fact, in this talk, I'm going to be talking about two different formulations of Bell's inequalities, one which is simpler, and the other one which I think illustrates the main point of Bell's inequalities in a more obvious way. So what is the main point of Bell's inequalities, and what is the main point of Bell's theorem? The main point is that they're used to prove that quantum mechanics, as a theory of nature, is a non-local theory. I'll say more about what I mean by a non-local theory later, but roughly what this means is that according to the laws of quantum mechanics, it is in principle possible for me to take an action at some point in space and in time, and for that action to have an effect, for that action to have an instantaneous effect arbitrarily far away from where I took that action. So that's what I'm going to mean by non-locality. And what Bell's theorem says is that quantum mechanics is indeed non-local, which is a rather surprising thing, that you can have an action taken here can have an effect arbitrarily far away. Now, the point of view that I'm going to be taking here is I'm going to require as little as possible previous knowledge about quantum mechanics. So Bell's inequality can be stated completely independently from quantum mechanics. In fact, it's an inequality in probability theory. So I'm going to state it that way. And there are going to be little bits and pieces that I need to add into the problem that do come from quantum theory. And when that happens, I'll explain what are the core points that need to be understood. So no previous knowledge about quantum mechanics is needed to understand what I'll be talking about here. Now, one of the reasons that I wanted to talk about Bell's inequalities is that the main point of Bell's inequalities and Bell's theorem is often misstated. So often what you will see is that the main consequence of Bell's inequality is that they show that in quantum mechanics, you cannot have local hidden variables, which is a vocabulary that I don't like so much. I'll talk a little bit more about what that means later on in the talk. But that is the way that things are usually presented. In fact, if you go to Wikipedia right now and type in Bell's inequality, the very first sentence that you'll see will say that it prevents the existence of local hidden variable theories. Now, this statement, I'll say more about that later. It's not untrue, but it really fails to capture the central point of Bell's theorem, which is that quantum mechanics is not local. Now, let me mention also that there has been a lot of renewed interest in these kinds of topics since the Nobel Prize was awarded in the fall of 2022 to 3 physicists who, along with their many collaborators, so these are Alain Aspect, John Clauser, and Anton Zeilinger, who, along with their many collaborators, experimentally proved that Bell's inequalities are violated. So they experimentally verified that Bell's theorem holds true in nature. Now, what I'll be talking about here is not the product of my own research. Everything that or essentially everything that I'll say here can be found on an excellent article that is available on Scholarpedia. This article was written by Shelley Goldstein, who's here in the audience, Norsen Tausman Zangi. If you have any further questions, there's a lot more in the article than what I'll be presenting here. If you're interested in learning more about all the various aspects of Bell's theorem, I highly recommend this Scholarpedia article. Okay, so so perhaps before I get into it, are there any questions at this stage?
I do have one question, which is, do we plan to talk about the kind of no hidden variable theorems that were proven by physicists previous to Bell in 1964?
No, I'm not going to mention the von Neumann result at all here. It's interesting, but not quite as interesting as Bell's inequality is, and really it misses the core point. All right, so let's so as I mentioned at the beginning of the introduction, I'm going to be talking about 2 different approaches to Bell's inequality, and 2 different Bell's inequalities, and 2 different approaches to Bell's theorem for reasons that I'll explain later. In the first part, I'm going to be talking about the simpler formulation of Bell's inequality, which tracks fairly closely to what Bell's original article from 1964 was, although the inequality that I'll be proving is actually a simplified version of what Bell proved in 1964. So in this 1964 paper, John Bell proved a theorem. I'm going to state that theorem essentially by giving the proof of the theorem, given that things are simple enough. And the proof of this theorem goes through 3 distinct steps. So let me go through each of these steps and get to the conclusion at the end of that. The first step of Bell's argument is the so-called EPR argument, which is due to Einstein, Podolsky, and Rosen, and was published in a paper in 1935. This EPR argument is sometimes called the EPR paradox. It's not a paradox, so this is what here I'll be calling it the EPR argument. So what does the EPR argument say? The EPR argument talks about a thought experiment, which I'll describe now. So let's imagine a made-up experiment that you don't actually need to do, but just imagine that this is the situation that we're considering. So we're going to have 2 observers. I gave these observers colorful names. So I have Alice on one side and Blurb on the other side. And what's important to understand the core issue of the EPR argument is that these 2 observers may be arbitrarily far away from each other. So in this fanciful example, I've decided that Alice is here on Earth, whereas the second observer, Blurb, is on a distant planet, which I've called Omicron Persei 8 in blatant attempt to reference Futurama jokes. Now, each of these observers has a physical system that they can they are free to experiment with. And in this example, I'm going to take the physical system as being simply an electron. So Alice has an electron and Blurb has an electron that they can both interact with. And the way that they're going to interact with their electrons is by measuring a property of that electron, which is called the spin of the electron. I'll say a little bit more now. So I have these two observers that are are spatially separated from each other. And what they're going to measure is the spin of an electron. Now, without going into details about what the spin of an electron is, let me just give you the minimal amount of information that you need to know about quantum spin in order to understand the argument. So there are three ingredients that I'm going to talk about. The first one is about what electron spin is. It's a property that can be measured. And in measuring the spin of the electron, you have the freedom of choosing the direction in which you want to measure the spin. The direction being an orientation in 3 dimensions. An orientation in 3 dimensions is an element of the 2-sphere. So the electron spin can be measured in any direction that you choose. And whatever direction that you choose, the outcome of your measurement is going to take one of 2 values, which are normalized here to +1 or -1. Okay, so when Alice measures the spin of her electron, say that she's measuring it in the vertical direction, the outcome is going to be either +1 or -1. Now, in this situation, so in this experimental setup, I'm going to add an extra ingredient to this. I'm going to assume that these 2 electrons are not just any 2 electrons, and in particular, I'm going to assume that they're not independent. So the way that I implement this is that at some point in the past, long before the experiments were done, these 2 electrons are going to be assumed to have been prepared in a special state that is called an entangled pair. For those of you that do have a background in quantum mechanics, this notation should clearly tell you what kind of state I'm talking about. But for those of you who don't have a background in quantum mechanics, suffice it to say that in this entangled state, the outcomes of spin measurements in the same direction are going to be perfectly anti-correlated. What that means is that if Alice and Blur both decide to measure their electrons in the vertical direction, say, then whatever Alice measures, either +1 or -1, Blurb will measure the opposite. So if Alice measures +1, Blurb will measure -1, and if Alice measures -1, then Blurb will measure +1. Right? There's perfect anti-correlation between the spin measurements. Now, this is something that is perfectly allowed or actually that the laws of quantum mechanics predict is possible and is doable, and this has been verified experimentally, that this is a kind of state that we can actually generate. So that's the second ingredient from quantum mechanics that I wanted to introduce. The third one, and this gets to the core of why Einstein, Podolsky, and Rosen were interested in this problem, or wrote a paper on this problem in the first place, is that when people think about quantum mechanics, there's an idea that is out there, which is that observable quantities don't actually exist until they're observed. So the outcome of a measurement does not exist before the measurement is performed. Now, this sounds a little bit crazy. It's not actually that crazy, because you can rephrase this idea by saying that the outcome of a measurement, so that you cannot perform a measurement without affecting the system. So you can't perform a measurement without affecting other measurements. And so the outcome of measurements don't all simultaneously exist independently of the measurement, because if you actually did a measurement, you might affect the outcomes of other experiments. And so that's essentially what this statement really means. And what Einstein, Podolsky, and Rosen set out to do is to show that this third point, it it does not square well with a principle that is very dear to many physicists to this day, and certainly was to physicists back then, that the world should be local. That there's friction between the fact that that observables don't have values before they're measured, and the fact that the world needs to behave in a local way. So let me be a little more precise about this. So let's assume that Alice and Blurb are performing their experiments, their measurements on the electrons. Let's assume that they're performing them at the same time, and that they're measuring the spin of the electron in the same direction. Now, if we assume that the world is local, what that means is that whatever Alice does to her electron when she performs the measurement, that cannot have an effect on the electron that Blurb is measuring, because the measurement is happening at the same time, and these two measurements are spatially separated, right? So there cannot be a causal relation between these two events. So assuming that the world is local, then whatever Alice does on her electron cannot affect what happens to Blurb's measurement. But we know, this was one of the postulates that we put in here, the outcomes of the measurements are going to be perfectly anti-correlated. What Blurb measures is the opposite of what Alice measures. Okay? So if Alice's action cannot be the event that triggers this anti-correlation, then this anti-correlation had to exist independently of the measurement. And the only way for this to be possible is if the outcome of the measurements was actually determined before the experiments were done. And so if the outcome of the measurements was determined independently of the existence of these measurements. This is what I'm going to be calling predetermined values for the spin of the electron. And this is what is sometimes called, what is oftentimes called in quantum mechanics as a hidden variable. The idea being that there's an extra hidden degree of freedom that forces the outcomes of experiments independently of the measurement. Shadi, you have a question?
Yes, I just wanted to. So when in relativity, the word "at the same time" doesn't make sense.
Yes.
So, but you don't need it. You just want to say that the events are spatially separated, right?
Exactly. So from a relativistic point of view, what I mean here is that they're spatially separated. So
that's all you need, right? That's okay.
Yeah, exactly. So I just want to say that these two events, there cannot be a causal relation between them. So spatially separated. Thank you. Okay, are there any further questions? Okay. So the basic, so the main takeaway of the EPR argument is that if we assume that the world is local, then necessarily electron spins need to have a value independently of whether those values are measured or not. So I'm going to summarize this here on the skeleton of the proof of Bell's theorem, just stating that the EPR argument states that if quantum mechanics is local, then observables, and in particular the value of electron spin, has to have a predetermined value, has to have a value independently of the measurement. Okay, so that's step one of Bell's theorem. So now let's move to step two. Step two is to prove an inequality that holds for a general probabilistic theory. And so let's state this inequality now. So we're going to consider the exact same imagined experimental setup where we have two observers that are very far away from each other that are experimenting on an entangled pair of electrons. Okay. Now, yes, so as I mentioned, spin can be measured in any direction in 3 dimensions. I've represented this graphically here by representing the measurement device that Alice and the measurement device that Blurb use. It has a knob here. That knob is a parameter that can be adjusted by Alice and Blurb. So that knob represents in which direction Alice and Blurb are going to be measuring the spins of their electrons. And in the setup that I'm going to think of for stating this first version of Bell's inequality, I'm going to assume that Alice and Blurb each make three separate measurements. And Alice and Blurb's measurements are done in the same directions, but the three measurement that each of them do can change direction. So for instance, Alice might measure first the spin of the electron in the vertical direction, and then at an angle of 2 pi over 3 from the vertical, and then at another angle of 2 pi over 3 from the vertical. And Blurb measures the same direction. So the vertical, 2 pi over 3, and minus 2 pi over 3. Now, when they perform these measurements, they're going to get outcomes. I'm going to denote the outcomes by z's. So Alice, so the outcomes on Alice's side are denoted by z superscript a, makes three measurements that give the outcomes z1, z2, and z3. Now, the outcomes of these measurements, as I mentioned, are either -1 or +1. And same for Blurb, the outcomes of the measurements are either -1 or +1. Now, these outcomes, from the point of view of the experiment, are going to be treated as random variables. Right? So, given the electrons in this entangled state, if all we know is this is the state, then we don't know what the outcomes of the measurements are. So let's suppose that there is a probability that gives us rules which of -1 and +1 these values of z can take. So all of these z's are going to be assumed to be random variables that are distributed according to a probability distribution, capital P. Now, what's important here is that this is a probability distribution over all of these values simultaneously. Right? It's the joint probability distribution over all of these random variables, which means that all of these experimental outcomes, they exist simultaneously. They all exist within the same probability space, which is what I meant earlier by them having predetermined values, in the sense that you can give an actual value to each of these measurements independently of whether those measurements are done or whether they're not done. Right? So that's the crucial assumption here, and that's how Bell's inequality relates to this notion of measurement outcomes having predetermined values. They're all distributed according to one probability distribution. And I'm going to add one ingredient from the quantum mechanical setup that I was interested in that, as I mentioned, the outcomes of experiments have to be perfectly anti-correlated between Alice and Blurb. So what that means is that with probability 1, zi for Alice is going to be different from zi for Blurb. There are only two values here, so different means opposite here. Okay? So that's the setup. Let's, given this setup, let's prove an inequality for probabilities of certain events. Now, the proof that I'm going to give, this is not Bell's original proof, but it's the simplest proof that I know of, and it just uses the pigeonhole principle. By the pigeonhole principle, we know that the outcomes of measurements can only take one of two values, right? Either +1 or -1, which means that if I consider three measurements, necessarily at least two of those measurements are going to agree. Right? So I measure things 3 times, I might get plus plus minus, have two pluses, or plus minus minus, or minus plus minus, or plus plus plus. In any case, by the pigeonhole principle, at least two of those measurements are going to have to agree. What that means is that if I look at the probability that 1 and 2 agree, plus the probability that 1 and 3 agree, plus the probability that 2 and 3 agree, it's for certain at least one of these events is going to be true. So this sum of probabilities needs necessarily to be larger or equal to 1. Right? But now, so all of this was on Alice's side. Now I can link Alice's side to Blurb's side by using the fact that A and B are perfectly anti-correlated. Right? So whatever Alice measures, Blurb measures the opposite, which means that the probability that zi for Alice is equal to zj for Alice is the same as the probability that zi for Alice is different from zj for Blurb, right? Because these two are certainly, or almost certainly, different from each other, opposite. Which means that I can rewrite this inequality as the probability that Z1 for Alice is different from Z2 for Blurb, plus the probability that Z1 for Alice is different from Z3 for Blurb, plus the probability that Z2 for Alice is different from Z3 for Blurb. This sum of probabilities needs to be larger or equal to 1. Okay. Shelley, you have a comment?
No, I have no comment.
Okay, sorry. You unmuted yourself, so I assumed you had a comment. Sorry. Okay, so this is an inequality, which I'm going to call a Bell inequality. Okay, so that's step 2 of Bell's theorem that states that under the assumption that we have this joint probability distribution for the outcomes of these 6 measurements, right, which is an assumption that I'm writing here as spins have predetermined values. Under that assumption, we get an inequality involving these 3 probabilities.
These are measurements on different pairs of electrons.
So these are hypothetical measurements that don't necessarily need to be done, right? So I'm thinking that the outcomes of these measurements exist independently of whether they're done or not, right? And so these are just hypothetical measurements.
But it's a particular pair of electrons.
Yes, on a particular pair of electrons, on one pair of electrons. Yes, that's important.
But are you assuming that you can physically do these measurements?
I think it's not so. I can do these measurements, but I don't think that it's necessary that I actually have a device that can do these. So within the theory,
Experimental test requires you be able to do them, of course.
I'm sorry?
The experimental test that people got the Nobel Prize for certainly requires that you be able to do
right. So
measurements.
So all of this has been verified experimentally. So yes, these are possible, but
these are the same pair of electrons, measurements done at different times, or what? I don't, or is
right. So as far as I know, what the experiments, the inequality that the experiments are violating is the CHSH inequality that I'm going to be talking about later. That does not, for which you really do not need to. So there isn't this picture of having three different measurements, and you really don't need to worry about in which order the measurements are done and on which electrons they're done. So here, these are, in the assumption here, we're just imagining that what if it is possible for these measurements to actually have a value. And then if you want to do experiments on this, you do experiments with different pairs of electrons that you assume are all in the same state. So it shouldn't really matter which one you're doing the experiment on.
excuse me, this is a crucial point.
Yes. And as we'll see for the CHSH inequality, which is the one that is experimentally verified, that experimentalists directly verify, there's no problem with doing that. It's the theory takes into account the fact that you may be working on different pairs of electrons. It doesn't matter.
But at this point, shouldn't one be clear about this? Because people would say, yes, you do the measurements presumably consecutively in time, and the first measurement influences the second, etc. They're not really independent.
Mm-hmm. Right. Yes, absolutely. But again, the argument here is to prove or disprove that it is possible for these measurements to have a value independently of whether they're done or not. Right. So so I think this inequality is more interesting as being part of a thought experiment, which is I believe why the CHSH inequality was introduced, because it was one that was more readily verifiable by experiments.
One thing that's crucial here is what you need to be able to check is each of the individual probability statements. You don't have to, you can't check, according to quantum mechanics, all three of the statements there and on the same pair of electrons at the same time. But each of these probability statements are statements you could check in quantum mechanics.
Yeah, exactly. And if you wanted to check each of them independently, you would need a new pair for each measurement. But if the pairs are in the same state, then according to the laws of quantum mechanics, these probabilities should be the same.
And in any case, these probabilities, each one separately, are standard quantum mechanical probabilities. I think most physicists would agree on what the probabilities are for each of the terms, the three terms there.
Yeah. Any further questions before I move on? All right, so we've gone through step 1 and step 2. Step 1 says that if quantum mechanics is local, then spins have to have predetermined values. And then step 2 says that if spins have predetermined values, then this inequality needs to hold true. Now, step 3 is to check that according to the laws of quantum mechanics, this combination of probabilities does not satisfy the inequality. So let's see how that works. So here, as I promised, I'm not going to require any quantum mechanics, so I'm not going to go through the computation in detail. Those of you who do have a background in quantum mechanics and who want to do this computation, it is very simple. It is this computation is done on a single pair of electrons, where you're performing a single measurement on Alice's electron and a single measurement on Blurb's electron. And what you're computing is the probability that the outcome of the measurement on Alice's electron is different from the outcome of the probability on Blurb's electron in the directions that are sorry, let me come back, let me backtrack just a little bit. I need to make one thing more precise about this experiment. So the setup that I'm going to consider here is one in which I've fixed the orientation of measurement of the spin for Alice and Blurb's measurements. So what I'm going to assume to do this computation is that Alice's first measurement and Blurb's first measurement are vertical. Then the second measurement is at an angle 2 pi over 3, and the third measurement is at an angle minus 2 pi over 3. So when I say first, second, and third, I don't mean that these are done in a sequential order. I just mean that these are 3 possible measurements that they can do, and I've labeled them 1, 2, and 3. Right? So the way that I compute this probability is I say that Alice measures the spin of her electron in the direction that is specified by the index I. Blurb measures the spin of his electron in the direction that is specified by the index J. And then I compute the probability that the outcomes are different. So this is a standard computation in elementary quantum mechanics. And the output of this computation is that this probability is 1 plus the cosine of the angle in between the two measurements, which here is 2 pi over 3. So it's 1 plus cosine 2 pi over 3 divided by 2. Cosine 2 pi over 3 is minus 1/2. So this is 1 minus 1/2 over 2, which is 1/4. And this probability is the same, whatever the choice of two different directions that I take. So whatever choice of I and J, the probability comes out the same. So the sum of these three probabilities is 1/4 plus 1/4 plus 1/4. So that's 3/4, which is smaller than 1. Right? So the Bell inequality that was stated here, that this should be larger or equal to 1, according to the laws of quantum mechanics, I can come up with an experimental setup where the sum of these probabilities is not smaller than 1. Sorry, is not larger than 1. So what does that mean in the logical progression here? If I find an experiment in which this inequality is violated, then the right-hand side of this implication is violated, which means that the contrapose is useful, which means that if the right-hand side is violated, then necessarily that implies that the left-hand side is not true. So in particular, that means that spins do not have predetermined values. And if I plug that back into the EPR argument, again, I use the contrapose, spins don't have predetermined values, means that quantum mechanics is not local. Right, so the statement of Bell's theorem, going through these 3 steps, shows that according to quantum mechanics, nature is not local. Okay. So that's Bell's theorem, and that's how Bell presented his argument, presented the argument in the original 1964 paper, although in the original 1964 paper, the inequality that was here was a different one, but the point is exactly this. Now, I want to talk about a different formulation of Bell's inequality. And what I'd like to do first is to justify why I want to look at a different formulation of Bell's inequality. The first reason is perhaps Bell's original reason. It's a social one. That when Bell's paper came out in 1964, it got a lot of attention, but it wasn't understood properly by most of the people who were writing about the result after it was published. Right. So what we established here is we established non-locality by using Bell's inequality, and Bell's inequality was established under the assumption that the outcomes of the measurements exist independently of whether the measurements are done. Right. So the assumption was that all of the values of spin measurements are predetermined, are determined independently of the experiment. They simultaneously exist. Now, I did this with spin variables. You can actually do this in a more general setting, and you can show that the violation of Bell's inequality implies that you cannot have pre-existing values for the outcomes of non-commuting observables, for the outcomes of measurements of non-commuting observables. So
that's probably a little too strong, because before Bell proves his things in an earlier paper, actually, he gives examples where you do have pre-existing values for commuting observables in some very special, non-commuting observables in some very special situations, models in which you could have those values.
I see. Okay. So I'll amend the statement to say that in a generic setup, if you have non-commuting observables, you cannot generically have pre-existing values for the outcomes of all experiments. So one of the ways that this can be understood, and this has been written multiple times since 1960.
By the way, Ian, one of the examples I think that Bell gave is just the example of a single spin 1/2 particle, not a pair of spin 1/2 particles, but a single spin 1/2 particles. There are plenty of non-commuting observables there, but there you could have a hidden variable model.
Yes, that's correct. Yeah, because you can violate locality for free in a sense there.
But it's really because the Hilbert space is too small. It's only two-dimensional.
Right, exactly. Yeah. Okay. All right, but let me move on to, so the second point that I'm making is still perfectly true. Right, so one thing that people have written about the consequences of the violation of Bell's inequality is that it shows that you cannot have predetermined values in quantum mechanics, period. Right, and that, as we saw, that's not true. Right, the reason that so what led to Bell's inequality was saying that all observables have predetermined values at the same time. Right, so it's not, and the saying that there are no hidden variables means that there are no predetermined values at all. So there's a subtle difference between this, which wouldn't be very important if it weren't for the fact that there is actually an interpretation of quantum mechanics. There's a theory that agrees with all the predictions of quantum mechanics that does have so-called hidden variables for certain observables that commute. And that this is a perfectly valid theory. It's called Bohmian mechanics or de Broglie-Bohm theory. And so saying that Bell's inequality shows that there cannot be any hidden variables in quantum mechanics is just not true, because you can come up with an example where there are hidden variables. Okay. Now, there's another thing that is said, and as I mentioned in the beginning of this talk, this is what is said most often. And in fact, if you go to Wikipedia, that's the first thing that you'll read, is that the violation of Bell's inequality says that there are no local hidden variable theories. Well, what we saw is that the violation of Bell's inequality shows that there's no locality. So it's true that there are no local hidden variable theories, but it's true in a weird sense, right? So what does it mean if Bell's inequality is violated? That means that local hidden variables has to be false, which means that either the theory has to be non-local or there have to be no hidden variables, right? That's the natural thing to think if you're told that Bell's inequality implies local hidden variables. So from this point of view, violating Bell's inequalities shows that there are no local hidden variable theories, okay? But this is kind of like saying that the statement 1 is different from 2 or the earth is flat is a true statement. But it's true because 1 is different from 2. It has nothing to do with the fact that the earth is flat, right? So saying that the violation of Bell's inequality implies that there are no local hidden variable theories is true, but it's a bit misleading because really the violation of Bell's inequality is saying that it's the local part here, this local part of the statement that is not true. You don't need to think about hidden variables. So this is why I want to look at another statement of Bell's theorem, because it's useful from this point of view to have a statement that does not say anything about pre-existing values. It doesn't say anything about what people call hidden variables. It simply states that if you have a local theory, then you have an inequality that is violated by quantum mechanics. And that clearly just shows that quantum mechanics is not local. There are other reasons for looking at this other interpretation. One of them is that in order to prove Bell's theorem, so in order to show that quantum mechanics is non-local, I had to assume that there was a perfect anti-correlation between the outcomes of measurements. Now, nothing is ever really perfect. So the fact that quantum mechanics says that there's a perfect anti-correlation can never be verified experimentally, where the best thing that you can do experimentally is to check that there is a very strong anti-correlation. Now, you could make everything that I was talking earlier quantitative and say, okay, what if things are not perfectly correlated, then how do things change? But it turns out that there's a simpler way of stating Bell's theorem that does not assume perfect anti-correlation. And so that just takes care of that problem without needing to think about it further. So let's look at this new revisited, slightly more general statement of Bell's inequality, which actually appears in a paper by Bell himself from 1975, or in lecture note. So the setup that I'm going to be considering is similar to the one that I described before. So I have two observers that are very distant from each other, or that may be very distant from each other, that are manipulating physical systems and that can perform measurements on those physical systems. And that measurement device that they're using has a knob that they can tune to change what observable they're actually measuring. So let's formalize this. I have two observers, A and B, and each observer has a parameter on their measurement device that I denote by alpha for Alice and beta for Blurb. So for instance, this parameter could be choosing the direction in which you want to measure the spin. Now, these measurements are going to have outcomes, which I denote by XA and XB. Now, I'm being a little more general here because, again, quantum mechanics says that spin can take only one of two values, but nothing in nature is exact. So saying that it takes exactly two values is something that you can't possibly verify. So let's be even more general. Let's just say that XA and XB can take any value in some compact interval. Here I took -1 and 1 because you can always normalize a compact interval to -1 and 1. Right, so I'm even allowing more values for XA and XB. Now, again, XA and XB are going to be random variables that are distributed according to a probability distribution. But here there's a crucial difference with how I was presenting things before. What I'm looking at here is for every value of alpha and beta, there exists a probability distribution. Right? So this makes no assumption on whether the outcomes of experiments for different values of the parameters exist simultaneously. There is no probability distribution that looks at events involving measurements in different directions at the same time. Right? So there's no question here about about pre-existing values or hidden variables or however you want to call them. I'm just saying that you set the parameters on your measurement devices, and that gives you a probability distribution. Now, what I want to show is that locality implies Bell's inequality. That's what I want to show here. So in order to do that, I need a notion of locality. So let me first talk about a notion of locality, which is the wrong notion, but is perhaps the most intuitive thing to start out with. So I want whatever happens on A to be independent of whatever happens on B. Here's a way of doing this that is a bit ham-fisted, a bit too strong, is to say that the probability distribution, the joint probabilities distribution on XA and XB should factor into a probability distribution that only sees A and a probability distribution that only sees B. Now, this is a very strong statement of statistical independence, right? Where I'm saying that there can't even be correlations, between A and B. So it excludes the setup that I had talked about before, where there's a perfect anti-correlation in between the measurements of Alice and Blurb, right? So this is too strong. This is not we could make such an assumption, but it would reject lots of very viable experiments. So what we'll do instead is I'm going to add something extra to the setup. I'm going to add an extra parameter lambda, which you should think of lambda as standing for the underlying state of the two electrons, right? So lambda is a parameter that pertains to both A and B at the same time. That is not necessarily directly measurable to experiments. In fact, in the cases that we're interested in, it's not. And since it's not directly accessible to experimental measurements, we're going to assume that it's also a random variable that is distributed according to some probability distribution that I'm calling Q. But now, since lambda represents the underlying state of the system, I'm going to assume that the distribution of lambdas is independent of alpha and beta. After all, alpha and beta are just parameters that Alice and Blurb can freely choose, so it doesn't really make any sense to have the underlying state of the electron system depending on the choice of the parameters that Alice and Blurb have made. And now, in terms of this extra parameter lambda, I can express the notion of locality in terms of conditional probability by saying that conditioned on the value of this extra variable lambda, the probability of XA and XB factorizes into a probability for XA and a probability for XB. Now, the crucial point of this is that this is an assumption that allows us to treat the case that we discussed earlier, in which I have perfect anti-correlation. So Bell's inequality can be stated as follows. So it's now a theorem that, under the assumptions that I just described, so under this setup here. Yes, Larry.
I just wanted to ask, is the definition of locality that you provide here, is this the definition of the locality that most people doing research use?
No, and in fact, I should be a little more precise here. What I'm writing here is a consequence of locality rather than a definition of locality. So if you're interested in causality, then you need a definition of locality that is much more detailed than this. Here, this is if the usual notion of locality coming from causality, if that were true, then this probability, then this rule should hold. So that this factorization of probabilities will hold. So here in this discussion, I take it as a definition of locality because that's the only place where locality comes in. But really, it should be understood as a consequence of locality rather than a definition of it. So let me state Bell's inequality as a theorem now. Under this, so following the setup that I just presented, I have an inequality for expectation values of the product XA times XB. And these are expectation values in the probability distribution P sub alpha beta And so these expectation values depend on alpha and beta. And this combination here is just obtained by varying alpha and beta between these expectation values. So I'm looking at the expectation value with alpha beta minus alpha beta prime, absolute value, plus expectation value of alpha prime beta plus alpha prime beta prime. And the statement is that this is smaller or equal to 2. Now, the proof of this is fairly straightforward. I think because the time is short, I'm just going to gloss over it. If you're interested in details, the proof is done in full detail in my YouTube video. It's also available on Scholarpedia. And if you download the slides, the full proof is in these slides. So the basic ideas are you want to use locality, and locality is stated for the conditional probability distribution. So you decompose your expectation value over, you write it as a combination of the conditional expectation values, like this. Oops. Like this. Then you can use the locality condition to write this joint expectation as a product of expectations. And this allows you to in combinations that are of this form that have the same alpha, it allows you to factor out the A part of the expectation value. Right? And then you can bound out the A part just using the fact that the random variable is bounded by 1, so this expectation is also bounded by 1. So you can remove these as far as an upper bound is concerned. And then you end up with a combination that you can write in the form x minus y plus x plus y, where x and y are these two expectation values. And then you use a very simple fact about real numbers that if the absolute value of x and y are smaller than 1, then x minus y plus x plus y is smaller than 2. And so that concludes. So I went through this a bit quickly, but if you're interested in the details, I think that the structure that I gave you should be enough to reconstruct the proof yourself. So this is Bell's inequality stated as a theorem, assuming these assumptions that I discussed earlier. And now again, according to the laws of quantum mechanics, Bell's inequality is violated. So we can see this in the example of measuring electron spins, where alpha and beta, the parameters that are chosen, are the directions in which we're measuring the spin. A simple computation in quantum mechanics will tell you that this expectation value that we're interested in is minus alpha dot beta, where this is the usual dot product in R3, right? Alpha and beta are directions in R3. And this allows us to rewrite this combination of expectations in a very simple way that depends on alpha, alpha prime, beta, and beta prime. And then we can make choices for these alpha, alpha prime, beta, and beta prime. The worst choice, the one that maximizes this quantity, is the one in which beta is orthogonal to beta prime, and alpha is collinear with beta minus beta prime. The prime is collinear with beta plus beta prime. If you do that, very simple computation, these just turn into squares, and the cross terms vanish because of the orthogonality condition, and you just end up with each term being equal to square root of 2, which yields a total of 2 square roots of 2, which is larger than 2. So quantum mechanics violates Bell's inequality, which means, according to the theorem that I proved, that at least one of the assumptions needs to be wrong, or needs to be violated by quantum mechanics. And now let's go back and look at what our assumptions are. So these first two are not really assumptions. These are just experimental setups. I assume that the outcomes of measurements are random variables. Okay, that's, unless you want to throw out quantum mechanics, you can't really get rid of that. Then I assume that this extra parameter is distributed according to a probability distribution that is independent of alpha and beta. Alpha and beta are freely chosen, so this is not something that you can throw out either. So the only thing that you're left with is locality, and so necessarily the violation of Bell's inequality by quantum mechanics shows that locality needs to be abandoned in quantum mechanics, and that's just the way that it is. Now, yeah, I think I'll skip this last part. The last part that I wanted to mention is that in the discussion in part 1, I talked about EPR, and the argument that I made is a rigorous argument. it's not stated in a very formal way. With this setup, one can actually state EPR as a theorem in an extremely formal way, and it's quite satisfying and interesting. But I think I'll just skip that, and I'll stop here. And if there are any questions, I would be very happy to answer.
Okay, before we open the floor for questions, why don't we give a big round of applause for that seminar, because that was absolutely fantastic. Thank you very much for coming out here and speaking to us. Seeing a lot of clap hands emojis. I appreciate this. So yeah, let's open the floor now for questions. Feel free to just unmute your mic if you have any.
Yeah, I have just a brief comment. So that one thing you didn't mention that people also get confused about. So you said that the conclusion there are no local hidden variable theories is not untrue but misleading. But this is often, of course, also even compounded by people binding local with hidden variable, right? And local should be bound with theory. So the Bohmian mechanics, of course, has local hidden variables, namely the points of the positions of particles, and there's nothing more local than a point, right? But the theory is non-local. So this adds to the confusion in the literature.
Yeah, that's a very good point. I completely agree.
But ironically, there is a non-local hidden variable at play. It's just that it's not called the hidden variable, and that's the wave function.
Yeah, exactly.
Right. One thing that I didn't mention is that there are a lot of people who will rail against this idea of non-locality and say that Copenhagen quantum mechanics is the right way to do it, but any formulation of quantum mechanics is in fact not local. And Copenhagen is very explicitly not local because it has that wave function that is behaving in a completely non-local way. So yes.
By the way, I should comment then. The theorem you talked about at the end, the more formal one with the lambda, applies, of course, to quantum mechanics, straightforward Copenhagen as well. It's just that straightforward Copenhagen, lambda is just the wave function.
Yeah.
Of course,
Yeah,
it's
no,
non-local. The
yeah,
locality condition is violated.
Yeah, and the Copenhagen interpretation is of course, in some sense, a hidden variable theory, even though they are not called hidden variables. It's all the classical variables that Bohr needs, right, to describe experiments, right? So to make contact.
That's true too, yes.
So one question that I think I'd like to ask is, so Bell's inequality shows that there cannot be kind of simultaneously all three hidden, like the spin, the observable correlated to spin, that all three of them can't be a hidden variable. I'm not saying this correctly, so I apologize, but I think you know what I'm saying.
Yeah.
In that case, what kind of physical meaning is supposed to come from analyzing these observables?
So an interesting question is how fundamental, that is related to exactly this, is how fundamental is spin really? And the outcomes of measurements that are done in experiments where they measure spin, the question is, what are they actually measuring? And, you know, since Bell's inequality clearly shows that when you have something like spin, you cannot give it a classical interpretation. It cannot be something that is fundamental and that actually has a value independently of whether it's measured or not, which from a philosophical point of view, to me, means that there's really no other way than to say that spin is not a fundamental, that at least this notion of spin is not a fundamental ingredient in the theory. So the way that I would define spin is in the dimensionality of the wave function. That you have a particle that has spin when the wave function has several components. even though the mathematical treatment of spin as a you don't need spin to be a fundamental observable in order to understand what the outcomes of these experiments are.
I think Shelley would call a fundamental observable that you're talking about part of the ontology.
Ontology, exactly. It's the question is spin part of the ontology? And I would say probably not.
And I think my, follow-up question is, would that alone lead, would that on those grounds alone, that spin is not part of the ontology, does that lead researchers to reject Bohmian mechanics? And like, are there, like, I guess I'm trying to understand, what are their arguments about why spin needs to be part of the ontology?
Yeah, so one argument, one thing that I have heard is that, criticism of Bohmian mechanics that I have heard is that the only observable that is fundamental is position. But we're used to manipulating lots of things that are not position. And so that makes people unhappy. But ultimately, so a central claim of the Bohmian point of view is that ultimately anything that you really measure boils down to position at the end of the day. And so when you're measuring spin, what you're doing is you're passing a particle through a magnetic field and you're seeing if it goes up or if it goes down. So it's at the end of the day a measurement of position.
In a sense, though, the issue isn't with Bohmian mechanics here. It's that once you agree that with spin components, they cannot have pre-existing values, then you're not, when you talk about spin measurements, you're not really talking about measurements. Yeah. Measurement means finding something that's there already. If it's not something that's there, but it's somehow a number which is created, it's not a measurement. So even from an orthodox point of view, I mean, people talk about spin in a confused kind of way as if it was a fundamental quantity without any clear understanding of what that could possibly mean.
So, sorry, I'm asking many questions. But if whether a particle is spin up or spin down, that is not something that's part of the ontology. But the fact that electrons are spin 1/2, as opposed to other kinds of particles being spin inserts, fractional number here, that is still something that we consider to be part of the ontology, right?
Right.
Right, because that determines what the wave function is. Right, that determines if the wave function is a function that takes values in C or in C2 or in C3 or in C4.
So like you say, if you're doing a spin measurement, well, you're finding out something about the wave function, perhaps. I mean, the whole issue of measurement in quantum mechanics is a bit obscure. Associated with it, you have the measurement problem and where to value it. It's all just almost incoherent. But a good student of quantum mechanics learns not to worry about certain things and learns how to do the calculations, and then they're just fine. But what they're not fine about is they lose a sense of what it really means to genuinely understand something.
All right, I think we give Ian another big hand.
Thank you all for coming and for staying till the end.
So let's have lunch.
Yes, please.
Yes. All right. Thank you all very much for coming. We'll be glad to see you in a few weeks from now.